Hello everyone, good afternoon, and welcome to our talk about breaking SecureBoot with SMM. So just before we start, let us briefly introduce ourselves. So my name is Assaf Carlsbad. I'm a security researcher at Sentinel-1, and co-presenting this talk with me is my friend and colleague Itai Liba, who works with me in the same team. So let's start. This talk is basically divided into 4 parts. First, we will do a quick overview of what SMM is and how it operates under the hood. Then we will move on to talk about some common SMM vulnerabilities and also demonstrate a small tool we wrote that lets you hunt down these vulnerabilities in an automated fashion. Afterwards, Itai will take over and explain in detail how we managed to exploit some of these vulnerabilities up to the point where he completely breaks SecureBoot. And finally, we will conclude by talking about some potential mitigations to the underlying problems. So let's start with SMM. SMM stands for System Management Mode. It's one of the operating modes available on every Intel-compatible CPU, alongside some of the more familiar modes such as real mode, protected mode, long mode, and so on. And what's special about SMM is that this mode was designed specifically to be used by the firmware to handle low-level operations which has a wide effect. So common examples would be things like power management, thermal regulation, emulating legacy devices, and basically any other piece of proprietary code the OEM wants to put into the box. Now, from the perspective of security research, the reason we care so much about SMM is that SMM is considered to be highly privileged. So, according to the Intel model of privilege rings, we can actually think of SMM as being ring -2. And that makes it, in some sense, more powerful than the OS kernel at ring 0 and even the hypervisor at ring -1. So, some of the special capabilities of SMM are its ability to fully access all the physical memory of the machine. So, you might use that if you want to subvert an OS kernel or an hypervisor. You can also refresh the BIOS and therefore gain persistence on the machine. And in addition, you can do all of the above while being completely transparent to all the layers above you, which also gives you a lot of stealth. Nowadays, the security industry much better understands the risks that are involved with SMM code, and therefore there are many ongoing attempts to deprivilege it. And some of these attempts will be discussed towards the end of this talk. SMM runs from its own isolated address space called System Management RAM, or SMRAM for short. On modern platform, the de facto standard region of SMRAM is called TSEG, and among other things, it contains all the SMM binaries that were loaded by the firmware, the SMM stack and heap, the SMM save state area, which is where the CPU records its context when entering SMM, and also some architectural tables such as the GDT, IDT, page table, and so on. Now, the main premise of SMRAM is that normally it can be only accessed by code already running with SMM privileges. So the way this works is that usually the chipset provides some kind of configuration mechanism that lets you close and lock SMRAM. And when SMRAM is closed and locked, only attempts to access it that originate from SMM will be forwarded to the memory. All other attempts to access it from a non-SMM context will be remapped by the chipset or simply discarded. And that's basically how SMM gets its isolation. Another key concept we have to cover are system management interrupts, or SMIs for short. SMIs are the events that cause the processor to transition into SMM, and more precisely into a dedicated SMI handler, which is a function responsible for servicing the event. Now, from the hardware's perspective, there is only one global SMI handler, but as far as the firmware is concerned, it can register additional sub-handlers during boot time to handle more fine-grained situations. In the UEFI standard, SMI handlers are installed by calling a service called SMI handler register, and each SMI handler is assigned a GUID, which allows to identify it and also retrieve it later during runtime. SMIs can originate both asynchronously by hardware devices or synchronously by software running with ring 0 privileges. And these software SMIs are basically the SMM equivalent of a system call. The way these software SMIs work are that the caller first takes the GUID identifying the handler and also all the arguments for the call and packs them together in what's known as a communication buffer, or COM buffer for short. Then the physical address of the COM buffer is written into a global structure called SMM core private data. The address of SMM core private data is shared between SMM code and non-SMM code, and therefore we can use this structure to pass information between the two different CPU modes. Finally, after the contents of the communication buffer are serialized that way, the caller can write to IO port B2, which belongs to a small component called the APM controller. And this IO port basically asserts the SMI pin of the CPU and causes the hardware to transition into SMM. After transitioning to SMM, control flow eventually reaches a function called the SMM entry point. And the SMM entry point takes the address of the COM buffer and its size from the SMM core private data structure. And then it uses the GUID found at the beginning of the COM buffer to retrieve the actual handler that should be invoked. In the last phase, the handler is finally called, and now it can access all the caller provided arguments by inspecting the COM buffer parameter. So after we covered enough background information about SMM in general, let's move on to talk a little bit about SMM vulnerabilities. So when attacking SMM, probably one of the best attack surfaces are these software SMIs that I just described, and there are two main reasons for that. First, they can be triggered in a controlled fashion from a less privileged context, which is the OS. And secondly, the contents of the communication buffer are fully under the attacker's control, and that gives a lot of flexibility. Most of the attacks follow a pattern called the confused deputy problem, in which the privileged SMI handler is somehow tricked or manipulated into doing something it shouldn't be doing. And that might include branching out the contents of SMRAM, or maybe leaking out the contents of SMRAM, or corrupting the contents of SMRAM. In this presentation, we will talk only about one such attack, and that revolves around the usage of pointers that are nested within the communication buffer. So in most cases, the communication buffer only holds data used by the handler, but from time to time there is also a pointer that is nested within it. And if the handler operates on the pointer without first sanitizing it, that can lead to a breach of the SMM security domain. So to better understand the issue, let's take a look at a concrete SMI handler, which is very simple. As you can see, the handler begins by taking the first field out of the COM buffer and treating it as some kind of an operation code field that tells the handler what it should do next. We can also see the valid values for this opcode are either 0, 2, or 3. And if for some reason the actual value differs, then the default clause of the handler will be executed. And the default clause actually takes the second field out of the COM buffer, interprets it as a pointer, and then writes a status variable to the pointed memory location. So let's see how an attacker can exploit this handler. So to exploit this, the attacker would first craft a communication buffer, which is comprised out of these two fields, and then write the serialized COM buffer into a location accessible to him outside of SMRAM. Then the attacker will move on to trigger the vulnerable SMI handler. The SMI handler will then inspect the opcode field to determine what it should do next. But since this field is under the attacker's control, he or she could choose an invalid value, say 4, and that will force the handler to fall back into the default clause. In the default clause, we know the handler will fetch a pointer out of the COM buffer, and since this pointer field is also under the attacker's control, he or she could choose an address that resides in SMRAM and therefore cause corruption at that particular address, which is obviously a very bad thing. So to mitigate these issues, SMI handlers are always expected to sanitize all the pointers nested within the communication buffer to make sure they do not overlap with SMRAM. And to do so, they can use a small utility function from EDK2 called SMM is buffer outside SMM valid, which does exactly that. So basically, we've seen this error keeps repeating itself over and over again. And at some point, we decided we should write an automated detection for it. So after several months of development, we ended up with this small tool that we call a Brick. And Brick is basically an automated static analysis tool that lets you hunt down SMM-related vulnerabilities. This tool is primarily based on IDA, and so far it managed to produce 13 different CVEs, affecting most of the well-known vendors in the industry. And most importantly, this tool is already open source and available on GitHub, so you can start using it yourself and maybe uncover vulnerabilities in your own firmware. So let's see a quick demo of Brick in action. Now, most of the time we use Brick to scan entire BIOS images, but in this demo we wanted to keep it short, so we are just scanning one particular SMM binary, which we extracted out of Dell Latitude laptop. So let's take a look at the demo. So basically, Brick is written in Python, so executing it is just a matter of running this very simple command line. And right now it executes IDA in the background, and first it lets the auto-analysis complete. That should take a couple of seconds. And after the initial auto-analysis completes, it basically moves on to run a bunch of custom IDA Python scripts. And these IDA Python scripts employ a wide range of heuristics and attempts to pinpoint potential vulnerabilities and anti-patterns inside the SMM code. That should take roughly 1 minute to complete. And after the analysis completes, all the results are basically dumped into an HTML report file that you can view. So after scanning, we open this HTML report file, and one of the lines immediately drew our attention. And I'm talking, of course, about this line here. So basically, Brick tells us it managed to find one SMI handler that doesn't sanitize pointers nested within the communication buffer. So how did Brick get to this conclusion? So to answer this question, we will now walk you through the individual phases of running Brick and gradually see how the detection logic builds up. So at the beginning, we are at what's known as phase 0. Phase 0 is just a snapshot of the IDA database after the initial auto-analysis completed, but before any Brick-related code got a chance to run. After it, we have the first Brick module that is called to handle any input file, and that's called the preprocessor. So the preprocessor basically sets up the ground for the next modules in the chain, and most importantly, it traverses the EDK2 repository and attempts to import as many UEFI protocol definitions as possible into the database. Now, for those of you who are not familiar with all the shenanigans of UEFI, Protocols are basically the building block that allows different modules to communicate with each other. So modules can either produce protocols or consume protocols. So if you're a producer, you would use a service such as SMM install protocol interface to expose a protocol, where under the hood, a protocol is just a GUID identifying it and an associated interface, which usually takes the form of a vtable. If you're a consumer, on the other hand, you utilize protocols installed by other modules, and you use services such as SMM locate protocol to do so. So you pass the GUID of the protocol you're interested in, and as a response, you get back the interface pointer, and afterwards you can use that interface pointer to invoke all the functions associated with the interface. So back to the preprocessor. After the preprocessor runs, the database is basically filled with thousands of these protocol definitions. Among them, we can find one that is called PCH SPI protocol, and this protocol will play a vital part in the next few slides. So following the preprocessor, Brick moves on to load and run an IDA plugin called EFI Explorer. And the EFI Explorer is basically the de facto standard way of analyzing UEFI binaries in IDA. And to demonstrate the capabilities of this tool, here we have some function before EFI Explorer analyzed it. And this is the very same function afterwards. So we can see EFI Explorer takes care of things such as identifying calls to SMM-related services, identifying known UEFI GUIDs, and also assigning correct types to interface pointers. And this is a rather new addition to the tool, and the way it works is that EFI Explorer managed to identify a call to SMM locate protocol, and they managed to identify the GUID as PCH SPI protocol GUID, and therefore it deduces that the corresponding interface should be of type pointer to PCH SPI protocol. And it just so happens to be that this particular type definition was imported earlier by the preprocessor, and therefore this typecasting actually works. Last but not least, EFI Explorer is also capable of identifying SMI handlers that are installed by the image. And in this particular case, there is only one such handler. And this handler actually makes use of the PCH SPI protocol, which is also a fact we will visit again later. Now, before moving on, we need to elaborate a bit about one protocol called the EFI SMM Access 2 protocol. So basically, this protocol is used to control the visibility of SMRAM on the platform. And as such, it exposes the respective methods to open, close, and lock SMRAM. In addition to those three, it exports yet another method called getCapabilities. And getCapabilities is actually used to query the memory controller about the location of SMRAM in physical memory. So when you call this method, you get in response an array of structures of type EFI SMRAM descriptor, where each SMRAM descriptor holds information about one active SMRAM region and includes important information such as its base address, its size, state, attributes, and so on. Now, what matters for our purposes is to know that these SMRAM descriptors are actually used internally by functions such as SMM is buffer outside SMM valid to determine if the caller provided buffer is safe or not. So, back to Brick. The next module that is called to process the input file is called the post-processor. And the post-processor completes the analysis performed earlier by EFI Explorer. And as part of its operation, it goes through all the calls to getCapabilities and simply marks the SMRAM descriptors that were returned by the call. And the importance of this operation will be explained shortly. Okay, so just as a quick reminder, basically what we are looking for are SMI handlers that don't sanitize pointers nested within their communication buffer. But for that to work, we first have to figure out whether or not the COM buffer holds any nested pointers in the first place. So normally we can do it manually as part of the reverse engineering process. But in this case, in the case of Brick, we needed to be able to do that automatically. So to do so, we leverage yet another IDA plugin called Hexray's Code Explorer. And this plugin lets you reconstruct the internal layout of structures used by the program. So we apply this plugin to the COM buffer, and basically that lets you transform a row pointer notation, as can be seen here, into a much more comprehensible notation, which is also aware of individual members. And even more importantly, along the process, Hexray's Code Explorer also extrapolates the types associated with different members. And in this case, it found out that two members, namely field 14 and field 1C, are actually pointers by themselves. So let's understand how we got to this conclusion. So from the code of the handler, we can see that at some point, both these fields, field 14 and field 1C, are being passed as the base address and region size parameters of the get region address method, which is also exported by the PCH SPI protocol. And based on the definition of this method, which was again imported earlier by the preprocessor, we know these two parameters are actually pointers. And therefore we can deduce that the respective pointers in the COM buffer must be pointers as well. So now that it knows the COM buffer does contain some nested pointers, Brick has to make sure that these pointers are being sanitized properly. Usually that boils down to first identifying SMM is buffer outside SMM valid inside the compiled binary, and then checking to see if all the nested pointers are being covered by it. So to identify SMM is buffer outside SMM valid, we compiled a simple heuristic, which is made up of 3 different conditions. And Brick will basically iterate over all the functions in the IDA database, and will search for a function that matches all 3. So the heuristic is basically pretty simple and asserts that first, the candidate function must reference one of the SMRAM descriptors. Remember that all these descriptors were marked earlier by the post-processor, and therefore at this phase, checking for cross-references between functions and descriptors is actually pretty easy. Next, it checks the arguments of the function, and more precisely expects the candidate function to receive 2 integer arguments, one used as the base address of the buffer and the second used to denote its size. And lastly, it checks that the function returns the Boolean value. Now from the perspective of the decompiler, Boolean values are just plain integers. So in order to make this distinction, Brick has to scan the AST of the function, visit all the return statements, and actually check that the returned value is either 0 or 1. Now, if all 3 conditions are met, then Brick stops the search and declares that a match was found. And now that it knows that SMM is buffer outside SMM valid is present in the binary, it has to make sure that all the pointers are being covered by it. So for that, it goes through all the calls to the function. And in this particular case, it found out that there is only one call to the function, which is actually used to validate the address of the COM buffer itself. And while this is a very important check that actually mitigates some other classes of vulnerabilities, it basically means nothing as far as nested pointers are concerned. So to summarize, using automation and some very simple heuristics, Brick managed to find an SMI handler that can be invoked from a non-SMM context, that operates on attacker controllable pointers that are nested within the communication buffer, but unfortunately it does not utilize functions such as SMM is buffer outside SMM valid to sanitize these pointers before using them. So taking all 3 into account, this is very likely to be a vulnerability. And now I'll hand over to Itai, which will explain in detail how this vulnerability can be exploited.
Hi. So this part of the talk also have a few goals. First, we will explain the vulnerable function and show how we got to a write primitive. Then show how we can use the write primitive to get to a read primitive. From there, we will use the SMRAM we are able to read with the read primitive to get an execution. And finally, we will break SecureBoot security feature to allow us to load an unsigned OS loader and break any OS secure boot process. So Assaf showed us that the SMI handler of SPI SMM stub of that Dell computer we suspect that is vulnerable. The function itself, the SMI handler, uses the PCH SPI protocol. The protocol is used for SPI flash operations like read, write, and erase. The protocol functions are called with argument from the command buffer without any verification. We wish we could use the flash write function in the protocol for execution and persistency, but the flash content is signed and protected by bootguard. Writing unsigned code to the flash will prevent the system from booting, so that doesn't work for us. The flash read function is used to read a buffer from the flash to memory. We can set the SMI handler to call flash read. We can provide flash address, buffer size, and destination address. The function will write the flash contents to the destination without validating the destination address. We set the buffer argument to point to a location in SMRAM we wish to override. But we can only control the value being written by controlling the flash offset. To write arbitrary data, we can set the handler to call the flash read to read a block to normal RAM. So we can read the flash block. We can use the flash block to generate a dictionary mapping byte values to flash offsets, and use the dictionary to write what we want where we want. After understanding the write primitive, we wanted a read primitive so we can dump SMRAM. Usually SMRAM is not accessible to anyone. We found a way to get from a write to a read by adding our own SMI handler. There is a linked list of SMI handlers in the PySMM core UEFI module. The base address of PySMM core is exposed to the OS in the SMM core private data structure used for calling SMIs. The head of the linked list is a global variable in PySMM core, and since we have the image base, we know where it is. We can add our own handler by overwriting the pointer to the first entry. The linked list connects SMI entry structures. Each entry contains a linked list to SMI handler structures. Each SMI handler structure points to a function that serves the SMI. When called, the first argument of the function is the pointer back to the SMI handler structure, and that will be important later. We can create fake SMI entry and SMI handler structures in normal RAM. Then, we can use the write primitive to override the linked list head with the fake SMI entry physical address. In modern systems, SMM code must reside in SMRAM due to the use of the SMM code check mitigation. That means that the handler we will add must point to a function in SMRAM. We need to find a ROP chain or a function already in SMRAM segment we can use. We are looking for a memcopy-like function in PySMM core that we can use with the limited control we have over the arguments. We've found a function that only takes one argument and call memcopy to copy 16 bytes. The source and destination addresses are derived from the argument. If we can control that argument, we control memcopy. We can set the SMI handler to point to this function and extend the basic SMI handler structure with additional fields. The new fields will be used by the function to calculate the source and destination addresses for the memcopy. Since the structure is in normal RAM, we can modify the arguments before every invocation of the SMI. Now we can trigger the SMI repeatedly, read 16 bytes at a time, and dump SMRAM. To complete the exploitation, we wanted to be able to run arbitrary code in SMM. SMM code can only run in SMRAM, and in SMRAM, the code segments are non-writable and the data segments are non-executable. Do we need to look for a ROP chain to change the permission? No. We can disable the write protection by disabling the write protection bit in the CR0 register. Overwrite some existing SMM code with our shellcode and jump there. We found a ROP gadget in the SMRAM dump. Performing the stack pivot of the part of the rope is very complex, so we provided a detailed explanation in the GitHub repo. Here we can see the other stages of the chain. We store the frame buffer in memory so we can return to regular execution after the shellcode. We disable the write protect bit in CR0 by writing an hard-coded value to where the bit is set to 0. We copy the shellcode from normal memory to the code segment of PySMM core and return to the shellcode. Now that we can run arbitrary code, we would like to show an example of what can be done with it. We saw a lot of news about bootkits lately, but taking a closer look shows that they target old systems with no SecureBoot and bootguard support. We can use our SMM code execution to disable SecureBoot and allow the loading of an unsigned OS loader. On this system, there are two EFI variables for controlling SecureBoot. SecureBoot enable let the user set SecureBoot on and off in the BIOS, but it's not accessible during runtime. SecureBoot mode lets the user choose between deployed mode and audit mode. Deployed mode enforces SecureBoot. Audit mode verifies the signature but doesn't prevent the module from loading. SecureBoot mode is accessible during runtime, but it's write protected. To bypass the SecureBoot write protection, we can use the SMM variable set variable function. This function bypasses the variable write protect check by setting a global flag. Since SMM is considered privileged, it's allowed to change write protected variables. We can set the value to audit mode, and that will allow us to load an unsigned OS loader. But we've found that setting the value to any other unsupported value allows the loading of the unsigned loaders, but adds the benefit of preventing the user from switching back to deployed mode in the BIOS setup. Let's see that in a demo. So we can see that SecureBoot is enabled and in deployed mode. Now we can try to load an unsigned OS loader, and we get an error message. Now we can boot to Linux and execute our exploit. That's it. It's all done. We can restart and try to load the unsigned loader again. Now it's successful. Let's see the changes in the BIOS setup. We can see that SecureBoot is enabled, but deployed mode is off. If we try to re-enable deployed mode, we can see that it doesn't work. We can still boot to the unsigned OS loader. All right. A little bit about the bug. We've reported the bug to Dell. Dell informed us that the bug is in Intel's BIOS reference code. So we reported the bug to Intel. Intel acknowledged with 2 CVs. Intel asked for extra time before the disclosure to allow all the vendors time to update their BIOSes. The bug affected many Intel products, which means that we can encounter similar bugs on many systems from different vendors. We've already discovered and were able to exploit a similar bug on a gigabyte UEFI BIOS. From all that exploitation work, we came up with quite a few tools and techniques, so let's talk a little bit about them. So using chipsec from Linux and Windows is great for UEFI exploration, but when working on exploitation, it's very limiting because you have to boot to an OS every time. We can use EFI shell. It boots very quickly. EFI shell supports executing a shell script at startup. That's very useful for automation. However, EFI shell waits 5 seconds before executing the shell script. So we found it useful to recompile EFI shell with no delay, and that allows for much quicker automation. We can use chipsec in EFI shell, but we found that it's even quicker to use MicroPython. There's a MicroPython implementation for EFI shell in the EDK2 staging repo, but it doesn't have a quick way to deal with large memory buffers. So we've added support for reading and writing using Python's byte data type. It can be found in my GitHub repo. Here is an example of MicroPython code calling a function from a UEFI protocol, something that is very hard to do with chipsec. PitchPy is a small assembler for Python that was relatively easy to port to MicroPython. And here we can see an example of PitchPy assembling a small shellcode. We can also see that the shellcode variable is using the added bytes access memory type that we talked about already. While working on exploitation, before restoring to normal execution, we need a way to return information from SMM before the computer hangs. We were writing information to a hard-coded physical address and using a USB 3380 board with a PCI latch from another computer, reading the physical memory and getting debug information out that way. When messing with BIOS, writing protected variables directly to flash, overriding modules, eventually you end up with bricked systems. In this case, flash programmers and hot air stations are definitely your friends. Now we can talk a little bit about mitigations and what would have prevented us from exploiting this vulnerability. So Intel BootGuard is a relatively new technology that complements SecureBoot. While SecureBoot ensures that the OS loader is signed, BootGuard ensures that the BIOS is signed. BootGuard works by storing the vendor's public keys in the PCH. On every boot, the PCH verifies that the firmware is indeed signed by the vendor. Because of Intel's BootGuard, we didn't look into writing directly to the flash. We should mention that other researchers did show that on some system, BootGuard isn't configured correctly, and then they were able to write modules into a boot-guarded BIOS. New SMM mitigations were added to the Intel vPro platform, starting at the 8th generation, Coffee Lake. The new mitigations include CR0 lock, which would have prevented us from writing on SMM code segments. We think it is a good idea if Intel added these mitigations to all its processors and not just the vPro line. Multiple SMRAM addresses are exposed to the OS via the SMM core private data structure. While by design, they help the exploitation of SMM vulnerabilities, and we think it can be avoided by a small number of changes in the EDK2 project. In our exploit, we added a handler by overwriting the first member pointer in the SMI entry linked list. The new SMI entry is stored in normal RAM. The code assumes that the entries are in SMRAM, but does not validate this assumption. This can be fixed by verifying that every entry and handler of pointers are in SMRAM. We are trying to push this mitigation to the EDK2 project. I'll give you Assaf back to talk a little bit about references.
Yeah, so just before concluding, we wanted to give you a few references for future reading. So first of all, we have some links both to Brick, which is the automated scanning tool that I showed you later, and an additional repo for the exploit code, all the tools that Itai mentioned, and some additional explanations for the ROP chain, which was pretty complex. Then we have a blog post series of 6 parts that we wrote about UEFI and SMM security. It starts from like baby steps of how to dump the BIOS from the SPI chip and ends up with exploiting these SMM vulnerabilities. And finally, we have some other references that were written by other researchers, and we used these references extensively during our research to learn about the topic and get into it, basically. And that's it for this talk. So thank you very much for your attention, and have a pleasant conference.
Thank you guys. Thank you for the presentation. Is there any questions?
There's one there.
Oof. Where are you? Okay.
So from what I understood, you were debugging on a real machine because you were using a PCI Leech to get debug information. So is there any emulator or a tool that could help you to emulate the exploit, the exploited code, so you don't have to break device?
So yes, there is. We did work on adding UEFI support to Python an environment, Python environment for emulating CPUs and OSs called chilling. So we could work on this vulnerability in chilling, and we could try the exploit, but the exploit part and being able to come back from restore execution and stuff like that you have to do on a real machine. Saying that, after dumping SMRAM, we were able to load the relevant sections from our binary dump to the emulator and work on the exploitation in emulation as well.
And one more question here.
Hello. Hi. Very nice talk, by the way. So a very stupid question in reality. If the BIOS is password protected, when you then boot the system, do you have the same level of access and privileges to the SMM?
So a BIOS lock doesn't affect this vulnerability at all. We change the variables from the exploit.
Any more questions?
Thank you for the presentation. What next for you? Are you planning to exploit the ACPI stuff? Because, you know, inside the SMF, you have tons of ACPI regarding the power management. And with this, I think you can find a few things like unlocking some pages and so on. So I'm a bit interested to have a discussion with you regarding this. I don't know if you know what is ACPI stuff.
So we don't have a plan to continue this research, as far as I know.
Someone else? What?
Thanks for the talk. Very interesting. I'm kind of confused on how the rope chain gets started, because you only get to override one pointer.
Right. So we only override one pointer, but we do, and I said that the start of the rope chain is relatively complex, and there's a doc all about it in the GitHub repo, because we call the function multiple times and run around it. You better read the explanation.
Okay, thanks. So it's so simple.
More questions? If no, we can thank our speakers.
Thank you, everyone.